but he's a very able and competent person, and we'll get started right now. Thank you.
Okay. Thank you so much. It's great to be here. Yeah. This is my 6th or 7th time at the Texas show, and I'm always amazed at the following you guys have, because I do presentations all over the country, and Texas it's true. Things are bigger in Texas, and sure enough, your show always tends to be the biggest. Sorry? Fix this? Is it okay? Oh, sorry. Okay. All right. All right. So just a quick little story. So the presentation Dave just gave was great. Part of what I do at Infiltrator is work on large systems just like that. In fact, dealt with systems that are over 1 million gallons a day that we're putting water into the ground. So one I'm working on recently, has anyone heard of the Hanford site, state of Washington? Yes. That's where they developed the nuclear power, or not the power, nuclear bomb back in World War II, and they kind of made a whole little town out in the middle of nowhere, the Manhattan Project. And so there was a lot of bad stuff that got washed over the years of development there, and now they're trying to still clean it up. They're doing what they call a pump and treat system. They're going to pump the groundwater up and take the radium and the cadmium and all these other bad contaminants in there, treat it, and then put it back in the ground. So I get calls like this all the time from what I call big pipe engineers.
Okay, it is not lunch break. It is not lunch break. The 11 o'clock classes are starting in Brazos and downstairs in the Texas North and South room.
Okay. So
downstairs, there is an OSHA class and alternative drain field.
Okay, I think she's done. So anyway, I work on large projects all over the country, and a lot of time the call goes like this. I know it's a big pipe engineer.
Brazos is rise or safety. It is not lunch break.
Is she doing this to me on purpose? So usually the call goes like this. How much does your system cost per gallon? All right. So I know right away he's a big pipe guy or gal. Because when we deal with on-site wastewater systems, we know we don't really have a price per gallon. Right? The last system we just looked at, there's not 18 inches of dirt, right? The soil. Or do we have to import soil? Do we have to blast to put in the sewer lines to get it there a half mile away? So every site condition is so different with on-site wastewater that we don't have a price we can just give, oh yeah, it's 5 gallons per day or $5 per gallon of treatment. No, we can't really give that. So anyway, this engineer I'm working with, anyone heard of the company CH2M? It used to be CH2M Hill. All right, so big pipe guy. All right. And he's working on this system, and he goes, okay, I pump it and I treat it, and I got about 10 lines 100 feet long, and I'm doing 55,000 gallons a day, and I calculate this out. 3-foot wide trench, X number of trenches, and it's 75 gallons per day per square foot that he's trying to get rid of, even though it's clean water, right? But there's no way he's going to get this in the ground. He goes, no, it's not that much. It's really 10 gallons per day per square foot. I said, well, how are you doing this math? Well, I got my whole area, and then in that area I got a couple trenches. So they just don't understand. No, the first design boundary condition is getting the water into the soil. So I got him to revise the design, and we're down to 48 gallons per day per square foot. That's the best I could do. But with a caveat that says, look, you need to treat it as an investigative type system because they're putting in this new treatment system, and you're going to monitor it. You're going to put monitoring ports and have a provisional area off to the side that you boxed off and say possible future area of expansion. So anyway, the first presentation was great because you don't know what you don't know when you're getting into projects. So you always want to cover yourself. And the more you get into these projects, the more you learn how much the design engineer who's stamping the plan doesn't know. So anyway, I deal with a lot of projects like that with Infiltrator. So what I want to talk to you today about is alternative drain field technologies. And I think we had to change the title to call it Advanced and Alternative, because when I met Ron at NOWA, Ron Shusecki, he said, "Oh, Dennis, come over. We need you to come back and do another presentation. Here's your topic." And I said, "Oh, okay." And I went away. And I forget which one it was advanced or alternative, but then on the title of the presentation, it said something a little bit different. So, and we're going to talk about drain field stuff today. So questions anytime, please, jump right in. Now, I work for Infiltrator, so I try not to make this an Infiltrator talk at all. I try and keep it very generic and open-ended. So let's get into this a little bit here. All right, so we're going to talk a little bit about historical perspective, the legacy systems, as I call them, and we'll talk about two-stage treatment. We'll go over the products and talk a little bit about class 4 soils, which are a little challenging. All right, so let's give you the historical perspective. How did we get to where we are today? All right, so this device here was awesome. It was incredible. It did a great job of protecting public health. It didn't do so good in the cities because the cities were too many people and they just, storm water washed everything into the storm gutters and rivers and streams. People really got sick in the cities, but you'll see if you've ever studied any history, there were times in the cities where everyone got sick and everyone went out to the country. And that was the reason, because the city's going to handle it. So in the country, we did a great job until what happened? We introduced indoor plumbing. Right? So depending on where you were in the country, this may have been the late 1800s, may have been early 1900s. But at some point, indoor plumbing is introduced. So, it took all forms and fashions, but you see the outlet here and the one prior. Here, you can see here it says to septic or sewer, so everything went out. But, at the time, we still only had this. So where did the sewer line go out of the house? Well, typically it went right into the base of this thing, right? All right. And it was a nice pit, but what was the problem? Too much capacity, right? Too much water coming in. So then we jumped to this. Okay, we had the pit and the pit latrine of the outhouse, and then we said, okay, let's put in a septic tank to get rid of that because we don't need the building anymore. And then we put in the tile pipe. And the tile pipe at first, when they extended that out from the latrine, it was just open joint, dig a trench, open joint. And then someone came along and said, okay, we want to expand the capacity of that. How do we do that? Oh, let's throw in some gravel, let's throw in some stone. So that's kind of the evolution of a drain field. Indoor plumbing kind of forced it to occur. So what was the function of that media? Why do we put media in the trench? Storage. Here it is right here, and storage is one of them. Well, first of all, this comes right out of US EPA. It maintains the structure of the excavation. It exposes the applied wastewater to more infiltrative surface. Now, what this means is when we had that open joint pipe, it created more area. And then it provides storage. So that's kind of the function of what the media is. So stone is what we call a legacy system. It's from the last century. There are new products that we're in the 21st century. New products are available. Why are they available? Well, there's a lot of baggage that comes along with those legacy type systems. For example, the fines associated with the system are very detrimental to system performance. They'll wash down or fall down into the infiltrative surface and reduce the permeability. So they'll cut down your perk rate. You thought you had a decent soil, and now it's just been reduced even more. All right. So why do people still use aggregate? It's cheap. Okay. I think, what's our biggest barrier we face today? Change is what it is. All right, very good. Our biggest barrier we face is change. I gave a presentation similar where I had a similar slide last time. And one guy said, death and taxes. Another guy said his wife. And a bunch of the contractors, of course, said it's the regulators are the biggest barrier. But anyway, the biggest barrier faced is change. It really is change, right? Yet, I see change every day in stuff that we do, right? I mean, look at this. We got rid of the rotary dial phone, right? Everybody has a cell phone, right? Think of the change we do take part in. I say, heck, even look at a toothbrush. It's like, holy cow. This has been designed by NASA. I mean, it's got all these shapes and rotators and electricity to it. I mean, look at, everyone drives pickup trucks, right? I mean, holy cow, you got anti-lock brakes for safety, you got airbags. I mean, we really incorporate change in everything we do, yet some of us are still stuck in these legacy-type products from the last century. All right. So let's talk about the benefits of the different technologies that are out there. Well, first of all, they're aggregate free, or fines free, right? So they're your answer to clean gravel. A couple of states, one's a real stickler that sticks in my mind is Massachusetts. The regulators will, tell contractors to rip out the stone, it's too dirty. They actually have a little test. They scoop it up and they shake it if a certain percentage falls through. They have another one where they take it and they put it in the jar and they shake it up with water in it. And if it doesn't settle at a certain rate, rip it out. Rip it out. It's too dirty. Even though they require what they call double wash stone. You ever hear of such a thing? It's still coming out real dirty because if you wash it, you just get the top and you don't get much more. So these benefits apply to different people in different locations depending on where you're sitting on the fence. For example, if you're an engineer, you love the fact that it's engineered product. It's fixed dimensions. State of Virginia has this rule called 13 per 100. I say, hey, what's this 13 per 100? It's 13 tons per 100 foot of trench. Trench is 3 foot wide, 12 inches deep, 13 tons. So I finally was going back and forth Virginia after we had a big approval in Virginia. I was doing a lot of legwork there, putting on presentations, training people, training regulators. Finally, I'm on the plane. I just start doing the math. Okay. It works out to 9 inches of stone. All right. So they're, in effect, cheating 25%. Even though 13 per 100 was their rule of thumb they always used. So engineers want to know that they're getting, if they specify a trench 100 foot long, 3 foot wide, and X deep, they want to make sure they're getting it, so they know they're getting it. All right. Inspections. So again, regulators can easily inspect the system, and they just, count the length of what their product is. If they're in fixed lengths, for example, chambers can come, or panels as you know them here, can be 4 feet or 5 feet long. Easy flow bundles are 10 foot long. Everyone use sock pipe, that comes at a fixed length. So it's real easy to inspect, and you're getting the right height, the right width, and the right length. So it makes it easy to inspect. They also know, some contractors first didn't like panels as much because they had to dig their trenches level. Because if not, the chambers kind of went up and down, and the regulator would look and say, geez, man, the trench isn't level. Whereas he used to get away with that when he was doing aggregate trenches, right? But it's easily done these days. Everyone has a laser level, and contractors are pretty good with their equipment now, and it's easy to do. So not a big deal there. All right. You can offer, with alternative technology, shipping benefits, shipping, nesting ability to get products to you cheaper. If you ask the contractor, why would you use an alternative product? It really comes down to time, right? They know they can do it faster, quicker, and to them, time is money. So you're going to save on installation time, which saves labor, which saves cost. Rule number one from the manufacturer is, doesn't matter what your idea is, how great it is, if it doesn't meet the almighty dollar of saving cost in some way, whether it be time or material cost, it's never going to work. So contractors have discovered that. These products can be very lightweight, ideal for repairs. You're not damaging your site. I mean, think of the site where, okay, we're going to bring in stone because it's cheap, right? All right, we're going to dump it over here, big pile of stone. The dump trucks came, you had to wait for the dump trucks. Okay, they finally came, they dumped. Now you got to go scoop it up and then drive it over to there and dump it in the trench and come back and forth and back and forth as you dump. You just damage the whole site. Now, if it's a repair, I'm from New England, and everyone thinks they have like the Augusta National backyard, right? They have the best lawn, and oh my gosh, we don't want to damage it, right? So they don't care about the septic system. They only care when you leave the site, man, that grass better be looking good, right? So if you can really minimize the impact to the site, again, ideal for repairs, these alternative products can save you a lot of hassle with that. Field service, many manufacturers offer field assistance. Some products will offer increased storage capability. Again, engineers kind of like this for what I call peak flow event facilities. If you have a church, you have a facility like this. If you have, heck, we did Gillette Stadium, Foxborough. That has a chamber system underground, 1.2 million gallons a day, and it has the storage capacity to absorb that and then let it slowly meter out through the ground, infiltrate in over the course of time. All right, and again, we can minimize construction traffic to protect the soil from wheel compaction. All right. So what about nationally? What these gravelless products? And again, there's all different kinds of gravelless products. It's not just what my company has. But they're approved in all 50 states, and half of all the drain fields installed in the U.S. are alternative products. Okay. In fact, from our stats with Infiltrator, just chambers, just our chambers, 75% of all systems are installed in 9 states are gravelless. And then in 16 states, 50 to 75% of the inventory of systems being installed are Infiltrator chambers. Quite amazing. Now it is becoming the de facto conventional technology. All right. So I had this stage 1, stage 2. I want to talk to you a little bit about just the basic on-site wastewater treatment. And we have stage 1, what I call the septic tank. It's a great device. It's a great device because it requires 0 energy. All right. So here we have the tank, and is Texas a 2-compartment state? Yeah, all right. So the 2-compartment theory, and I say theory because I go to a state and I say, okay, you're a 2-compartment state. Show me your data why it's 2-compartment. What's the research? Why not 1 compartment? Doesn't exist. There's 2 studies done, and both of those are a little bit weak because one entered wastewater into septic tanks that went from grinder pumps. That was a little suspect because everything was kind of really blended up and wasn't settling so well to begin with. And the other study was done at the University of Washington, Dr. Seablum, which was a pretty decent study, but he looked at purely the physical aspects. There's a physical aspect of settling a piece of effluent, particle. So it's called Stokes' law. So that's the physical aspect. The problem is we have 2 things going on. We have the physical process of settling, and then we have the biological activity of anaerobic digestion, right? So the problem becomes they're in conflict with each other. As we're trying to settle this particle that's trying to slowly settle down, all of a sudden there's these bubbles coming up, and they're being resuspended because anaerobic digestion in the tank produces bubbles, right? Produces gas. All right. So that's the theory of a 2-compartment tank. If we can minimize the anaerobic digestion or maximize it to occur in the first compartment, and then the second compartment would be more a quiescent zone and settle out those little last particles that got through, then we'll have a cleaner effluent exiting the tank. So that's the theory of a 2-compartment tank. So what does the tank do for us? Well, again, it does a great job. Compared to what's coming in to what's exiting, you have 75 to 95% solids removal, fats, oils, and grease, great removal rates there, 85 to 95%. And the anaerobic digestion is going to take care of 65 to 80% of the BOD. And what it doesn't take care of, because the rate of anaerobic digestion is pretty slow, so we're actually going to accumulate solids faster than we decompose them. So hence, we have to pump a septic tank every 3 to 5 years is what we recommend. All right. So that's what the tank does. It does a great, great job. But as I tell everybody nationally when I give presentations on malfunction analysis, none of this stuff works here if it's not a low velocity environment. Right? Primary settling, primary treatment requires a low velocity environment. So for example, if we have that leaky fixture in the toilet, right, we have a continuous flow. If we have, I grew up, I'm the youngest of 6, so I had older sisters, and gosh darn, they're taking 2 showers a day and wearing 3 outfits. So if you got 3 teenage gals living at home and they're using a ton of water, then all of a sudden we're not settling out stuff. So what's going to happen over time is you're going to burp solids. You're going to burp them out. All right? And they're going to get out to that drain field, and they're going to end up plugging it up. So as I always say, tanks are cheap insurance. If you can go bigger, go bigger with the tanks. They can only help out. All right, so we talked about anaerobic digestion. That's the process where we take solids and we change it to gas form. So when we go back to that tank picture here, remember this tank is vented, right? Vented right through the house stack. Not only that, in a gravity situation with a tank and a drain field gravity, the drain field is vented right through this, right? And then this is vented right through this T and up and out. So as these solids are giving off gas and gas is coming out from the drain field, we can vent it off. So that's where all these gases here, carbon dioxide, methane, will vent off right through the house stack. All right. That's why, as John was giving the talk today about confined space and septic tanks, right? You don't ever want to go in the septic tank because of the gases are toxic. Okay, so we talked about the first stage of treatment, the septic tank, which does a wonderful job. We talked about the second stage treatment, which is what? The soil, right? The drain field. Okay, so how can the drain field, or how does the drain field do? Well, it's what we call the septic tank does primary treatment. The drain field, meaning the soils under the drain field, do tertiary treatment. All right, and we'll look at that. So where do we see that? There's many, many studies out there. I don't know if any of you done any, watched or researched any research on sand filters over time. I mean, it seems like every university has studied sand filters over and over. It's like why they keep studying it. It's already been done. Anyway, we look at the treatment level through 2 feet of sand media is pretty nice. And it's that basis of understanding that we set our separation distances to groundwater, that we know we're getting a certain level of treatment. So that's what Dr. Segrist did at the Colorado School of Mines, is he made what he called these big lysimeters, which is a fancy word for a big sandbox. And he actually had 4 of them, and he made them all very, very similar. So we had to test them with clean water to make sure there was no preferential pathways, made sure they're all the same. And then he applied 2 of these at stone and 2 of these at open chambers. But again, that doesn't really matter at this point. We're looking at the treatment available in these systems. All right. So he installs the system, applies wastewater, applies it over time, applies it for 48 weeks to reach steady state over and over and over. And you can see biomat development here. You can see it here into the soil. So what's going on there, that biomat? Is that biomat good or is that biomat bad? I hear good, I hear bad, I hear both.
It can be both.
It can be both? All right, so who said good? So why is it good? That's where it's treating it, right? Now, when biomat becomes bad is what I would argue that it's no longer biomat. Okay? That's when the homeowner abused it with the burping solids, and those solids get out in that drain field, and they plug up this interface here. They plug it up. But people still dig it up and say, oh man, look at that biomat. That plugged up the system. That's bad biomat. Well, yes, it's bad, but that was homeowner induced, whether it be garbage grinders or whatever they were doing in the home. They abused the system. But all systems should have a biomat, and biomats are good, and they should be healthy, and they should be thriving. So these are nice biomats here. So why are they good? Well, what happens here is when we introduce wastewater to soil, what are we doing? We're feeding bugs, right? This is just a wastewater treatment plant. It's underground, right? All those soil particles have a lot of surface area, a tremendous amount of surface area. The bugs are just waiting. They're waiting to be fed, and they just love it, right? A lot of surface area and food, and the bugs love it, and it forms a biomat. So why is that biomat good? Well, it's good because then it forms what we call the LTAR. Everyone hear the long-term acceptance rate, right? What is the application rate of the soil, of sand? Most states say, okay, 1 gallon per day per square foot in a sandy soil. Right? And it varies state to state, but that's just a good, nice round number. But the problem is if we were to apply clean water to that interface and it's a coarse sand, we could get 1,000 gallons per day per square foot through that. Right? The permeability. Right. So that's a one-shot permeability. We just did it for 1 day. Right. So the problem there is if we do that, then we just get water from point A to point B, which say is the down the bottom here, which would be the groundwater. We'd have no treatment. So this biomat actually holds the water up. So then we have unsaturated conditions below the system. So we have two-stage treatment right here in the drain field. We have anaerobic right at the biomat, and then we have aerobic below the system. And that aerobic system, that separation distance, is where that most of that treatment occurs. So with 2 feet of soil under the drain field, we're going to get rid of all those bad guys. The bad guys, I mean, it gets rid of BOD and TSS in probably the first 6 to 12 inches. That's not the issue. We can get rid of that real easy. It's those bad guys of viruses and pathogens we got to get rid of. All right. So that 2 feet of soil, as a water particle moves from, or a drop of water moves from here to here, it kind of, it might sit here for a day and then gets displaced by another, water droplet and moves over to here. So it'll be a long, torturous path. It might be, in this case, it was 12 days to get from point A to point B, all right, to hit to that 2 feet of groundwater, all right, because he could put in tracers and dyes, and he knows what it took in this case. So the overall theme here is the biomat is good. It's a good thing. Systems are designed for it. That's why we have the long-term acceptance rate. But yes, if the homeowner abuses it and that system gets sealed up, that's not good. But that to me isn't biomat. That's a clogging layer from the home. That's not a healthy biomat. So let's look at the studies here that he did. So he had 4 different lysimeters. 2 were at 2 feet to groundwater and 2 were at 3 feet to groundwater. So he's a research scientist and he's trying to answer the question, what should the separation distance be? Because some states it's 4 feet. Some counties in California it's 5 feet. State of Connecticut is 18 inches. All right. State of South Carolina is 6 inches. All right. So what should the separation distance be? So this is what he got. So if the septic tank effluent coming out of the septic tank for the BOD was a little over 200, TSS a little bit below 100, you could see the lysimeter percolate down at the bottom was pretty low. So it was about 82 to 84% removal on BOD. COD much, much higher. TSS up to 85%, or 85% there. And the fecal coliform, couple log removal there. And he had excellent virus removal. So, but the amazing thing was there was no differences between the lysimeters, whether it was 2 feet of groundwater or 3 feet to groundwater, whether it was the stone system installed or the chamber system installed. The chamber system was installed and loaded at a much, much higher rate to simulate what they call the reduction, to take that into account, because some regulators nationally had a concern that, the chamber system was reduced, so it's loaded at a higher loading rate per square foot, so maybe the pathogens and viruses are getting through, or maybe the BOD or TSS wasn't being treated as well. Well, there was really no difference in treatment. And Dr. Segrist goes on to explain this. Why? Why is there no difference in treatment? Well, because the soil has a tremendous ability to treat. Heck, it could even treat more, but that biomat is really a governor. It's regulating the amount of wastewater going through it. So it's limited by that biomat. Okay? And the important thing I like to say here, that all these systems, I don't care what the product is installed on the top, whether it be aggregate, whether it be any other type of advanced alternative drain field product, everything we talk about is really soil-based treatment system. At the end of the day, it's the soil that does the treatment. We just got to get the wastewater to the soil, get it to in more efficient ways with the alternative products where we can protect the soils, we minimize compaction, we get rid of the fines and everything else. But at the end of the day, it's the soil that does the treatment. Okay. So let's talk about these advanced drain field technologies. Well, 285 lists a bunch of them. Gravelless pipe is approved, mounded drain fields, and it had some other things here called wide excavation, evapotranspiration, LPD. So not only are there products, but there's types of installations that have been learned over time which fit different site conditions. For example, if you had a shallow depth of bedrock, maybe you can install a mound system. Right? That's one of your options. Right? There's other options as well, but that's one of them. So not only do we have just products, but we have drain field installation types as well. So of course we had the panels, easy flow, drip dispersal, and then we have the spray systems here. Did anybody do the spray systems? They seem to be real common in Texas. All right. I could tell you nationally, as I tell other people in other states what people do in other states. For example, in Texas, I might be in, like last week I was in Missouri, and said, well, they do a lot of spray in Texas. Like, oh, spray? You're kidding? They don't do that. Spray? What are they, crazy? That's nuts. So anyway, it's funny as I travel state to state. If I cross a political boundary, the laws of physics seem to change sometimes of what works and what doesn't work. So just a little bit about, sorry, I jumped ahead here, about Easy Flow. People seen Easy Flow? It's not too big in Texas, but it's just an engineered aggregate product. It's a polystyrene bundle. It's manufactured with recycled material. It's in netting. It's in 10-foot long bundles, and some of the bundles have a pipe in them and some don't. And in a 2-foot wide trench, this is the configuration. We call it the triangular configuration. So those are 10-inch bundles. And so this product rating is equivalent to a 2-foot wide trench. So if you had a 2-foot wide table of, it said number of bedrooms with a 2-foot wide trench, this is how many linear feet you need. It'd be the same with stone as it was for this product in this case. So the sizing is equivalent. Okay. This is an engineered aggregate, so there's no fines involved. Most states, this product is approved with a reduction. All right, and of course there's the panels and chambers. There's many sizes and models. We have a Texas design manual that shows all of them, and because there's different sizes, different chambers have different credit ratings accordingly, according to the height and width. Here we see a standard trench system, septic line coming out of the house to a tank, and then to a D-box, and then to a drain field. So very simple, very basic. Here's a typical trench. You have the CAD drawing, CAD layout. So you can have in this case, this is our high capacity chamber. It's a 3-foot wide product. Now, it's funny, the chamber really isn't 3 foot wide, but it's a 3-foot wide product. Just like anyone builds a house, a 2x4 is a 2x4, 2 inches by 4 inches? No. So our chamber is not 36 inches wide because your buckets are 36 inches wide, but if we had a 36-inch wide chamber, it wouldn't fit in the hole. Right? So we have to have a little bit of tolerance there. So with 12 inches of cover, you drive over these with the rubber tire backhoe, no problem. All right. We do have systems different than this one. That's what we call H20 traffic loaded systems. Anyone install any of those? All right. In that case, it's not the chamber that's H20, although we have an H20 cross section. The cross section goes like this. Dig a trench or a bed, depending on your design. Lay down 3 inches of stone, put on our H20 chamber, which is different than this chamber. It's the older models. Remember the 6 1/4 foot chambers? So those had a thicker wall section. It's virgin plastic. It's stronger plastic. These are recycled plastic. All right, so you put down 3 inches of stone, put the chambers down. You backfill with crushed stone. Okay, so we're using the stone for a structural known quantity to get a higher load rating. So after you do that, you'll put down some filter fabric so the fines stay out of the stone. You'll put down 12 inches of compacted material. Then you put a geogrid over that layer, and then another 6 inches of compacted material. So that's what we call an H20 load system. Anybody know what H20 stands for? The load rating, what that means? Anybody? 32,000 pounds per axle. Anybody have a rig that does that? Okay. You probably don't. Okay. It's a very, very high load. We use a contractor to do our structural testing. We will break axles. The H20 load rating somehow got carried over to the on-site world just because it was a known thing. It was known from bridge design. All right. So bridge design, H20 load rating makes sense because there's lives at stake. You know, we don't want a bridge to break. So anyway, it's a hypothetical load that structural engineers could put on a design, you know, put a point load, 32,000 pounds, and they can run their calculations. But in the real world, it does exist at times, but very, very rarely. So it's a very, very high load. I think it's way over designed for what we need to do, but unfortunately a lot of codes have just incorporated it because it was easy. It was something to grab that they could put in. So anyway, that's the story of H20 loading. So we have a Texas design manual. Many of you have seen it, but many manufacturers offer similar charts. If you have, you know, X type of soil and X number of bedrooms, then okay, this is the amount of product you need. So those are readily available. Again, many manufacturers, all their products offer the same thing. I just wanted to show you that. All right, so we talked about change, right? What change do we see? We're an Infiltrator, we're a national company. I can tell you, it's great to see some younger faces in the crowd, and the younger guys are, you know, more, I don't know, incorporate change and, you know, electronics and both into their business and everything else. But what we see is you don't need to have the huge triaxle dump truck. You don't need to be carrying the huge excavator behind it. Because now we see this more and more often. Heck, those younger kids who are ambitious, they get a heavy-duty pickup truck, they get a trailer, and there's their system. Off they go. Then maybe they have a mini excavator, they go grab that next. They don't need to have a big one. So they're in business. And they're in and they're out quick. And they can do a lot of systems per week. So this is the kind of change we see. You know, easy delivery, get in and out of the site, not waiting around for dump trucks to deliver stone. We've had many guys who made this change who have triaxle trucks, and they said that's great. They're still using their trucks to haul to other sites, other jobs, you know, small road jobs or a house excavation, bringing in material. They're still keeping those guys busy. So it's a way to expand his business. All right. So I wanted to talk to you here. Okay, what do we do here if we have this type of soil? All right. So this is a class 4 soil. What are my options?
What's the biomat do in the class 4 soil?
Biomat grows at the surface and stays at the surface. All right. So this is the story I was told about. I said, oh, why, you know, again, I come to Texas a lot. I love coming here. I said, why do you have spray? You know? Well, I was told it's because of soils like these, right? I mean, heck, we don't have spray in New England because we're blessed with the glacial, you know, period, and they deposited, you know, sands and gravels. We have a lot of bedrock, but anyway, we have a lot of rock, but we have sands and gravel, so there was never a need for spray, right? But you go through, you know, here the black belt, the gumbo clays, and they come all the way down Alabama, right through Mississippi, Louisiana, and come into parts of Texas, right all the way down to Houston. So I'd be the one to tell you, hey, I love to put in drain fields everywhere, but you can put in a drain field in this, and what's going to happen? It's not going to work. Right? So they had to resort, give me a solution, give me a solution. So somebody said, all right, let's spray it. Right? So by default in Texas, you probably had to spray because of these soils. Right? So what can we do here? Well, we go to chapter 285, and you can go to spray, right? And this is probably the most common thing we see. And spray is fine, spray is great as long as, it's designed and maintained regularly, and we have the chlorinator here. So here we have the trash tank, the treatment unit, the chlorinator, and then the pump tank, and then the spray heads. So very, very simple system, right? Very, very cost effective. But then we get, okay, what if a homeowner has a tight lot and doesn't, want to have kids play in the backyard, but we don't want to have spray? Well, what can we do? Well, you can go to an ET system, right? Anybody do ET? Okay. I don't think it's too common because it certainly wouldn't work in the Houston area or along the coast, right? Because for an ET system to work, the rate of evaporation has to be greater than the rate of rainfall. So pretty simple. And this is the quote right out of 285. I won't read the whole thing. But basically what you're looking for there is 100% of your water to go up, to evaporate, evapotranspirate. So the roots are going to uptake it, and the roots are great because it also get rid of the nutrients, the phosphorus and the nitrogen. But again, so it's just another kind of tool to have in your toolbox. If you're doing systems in western Texas where it's drier, that would be a good one. All right. You can also go to drip, right? Some great slides on the last presentation of drip. And again, trash tank, treatment unit, pump tank. What this doesn't show here is maintenance to get at the flushing mechanism and the filtering system. And then you go out to the drip field. And here we have a large drip field here. And you can see all the drip lines going in, coming back to the manifolds and the headers to allow it to pressurize equally. Raise of hands on drip. Who does drip? Okay, yeah, so it is pretty common. It's a great solution. Again, I got calls from all over the country. I told you the one about the big pipe guy says, hey, what's your cost per system per gallon? The other one we get is, how many of those chamber things do I need? Right, we got an 800 number, right? So people call us all the time. How many chambers do I need? So what would be your answer if you're sitting in my shoes? I don't know. Usually that call comes on a Friday afternoon because what do you think's happening? The homeowner's doing it with his buddy who has a backhoe. Oh, how many of those chambers? So my response is, hey, it says right on your permit how many you need. It's right there for you, right? Oh, well, how about what do you how many do you think I need? I only got two bathrooms. So anyway, I try and talk to them, and I just tell people, I said, look, you want to get a permit, you want to hire a licensed contractor because if anything ever goes wrong, you don't want to sell the house, you say you have a compliant system and everything. And so anyway, that's what I tell them, and usually they hang up a little mad at me. So anyway, drip is a great option. So the story with drip is if it is a designer or somebody else or a contractor who knows soils, and they say, well, gosh darn, it's some difficult soils. A lot of states still use the perk rate, use perk tests here. But perk rate, let's say, oh, geez, it's over 90 minutes per inch. I tell them, I said, look, that's a great system for drip. You want to go to drip. Because those systems, you try and dig in those class 4 soils and put in trenches. I mean, the soil is really smeared. There's not, I don't care what kind of contractor you are, just the equipment is going to smear it either way. So drip has its place, and it's a great, great system. Okay, you can also go to mounds, right, in the class 4 soils. Again, I don't know if it's too popular. Anyone do mounds? All right, yeah, not as popular as the spray or the drip. But it is an option, another tool for your toolbox. So the way the mound works is the bottom of the system here is what we call the basal area. So that would intersect right where it sits on top of the class 4 soil. So that infiltration rate has to match what that soil will accept. All right. So let's say the basal rate or the soil, the class 4 soil that is infiltrating, let's say it's a 0.2 soil or a 0.1 soil. That means that square footage I provide here, as that feathers out, my basal area is much, much bigger than my surface area on top because I'm applying septic tank effluent here to sand, at 1 gallon per day per square foot. So my system is this big. But then when I get down 2 feet below that, I intersect, now I have to get to 0.1 or 0.2 gallon per day per square foot. So that tapers out like a trapezoid, and that second interface, that second boundary condition where it hits the basal area is much, much bigger. So mounds are very, very popular in the Midwest. All right, anyone hear of the Wisconsin mound? The whole design theory for that was based out of the Midwest. So we do a lot of mounds in the Midwest. The Midwest has very, very challenging conditions. I think the toughest I've seen, other than extreme like Yukon territory, we design systems, Alaska, Alberta. But anyway, the Midwest is very tough because it's flat as a board, class 3, class 4 soils, and high water table, and cold weather. So they have a tough, tough go of it up there.
How do the mounds work in cold weather?
They still function the same. We don't see any freezing, any issues. They have to be designed appropriately, right? So you see, in Texas requires the mound to be pressurized, right, LPD, in the mound itself.
It is pressurized.
Yeah, you got to pressurize. So the rule of thumb is, it's beaten into my head when I was a young engineer. It was beaten into my head by the older engineers. He said to me, when the pump shuts off, all pipes must drain out. Okay. Now, that same condition holds true even in the warmer climates. Okay, so why is that? Well, because if we take wastewater and let it sit in a pipe, stuff grows. Slimes and ugly stuff. Anybody ever flushed a line? Except, a pressurized line? I mean, there's stuff that comes out of there like, whoa, big globs start coming out. So it's best to try and drain those lines out, whether you're in cold climate for frost conditions or warmer climate due to stuff that's going to grow, and then plug up your orifices. All right. So great question there, thanks. So we don't really see any issues with frost or freezing of septic systems in general because of the latent heat of that water. Okay, it keeps the system from freezing. Where I live, the frost, if you're going to build a foundation, 42 inches. All right. But all the septic systems are installed, 12, 18, 24 inches deep. They never freeze. They never freeze. And again, because it's that warm water coming from the house, the biological activity in the tank, that keeps that system from freezing. So one of the I talked about cold weather climate, and I talked about engineers calling me up about doing large systems. So I get a call. This was back when the Canadian tar sands were really hot and moving along, early 2000s. So a guy calls me up. Says, hey, I got a man camp, 2,000 men. What do I need? All right. So what do you say to him? I said, I'm an engineer. Okay, get out my pad. Okay, what do you got for soils? Okay, what's your design flow for 2,000 people? Oh, hey, look, you're going to have to go and get this thing approved. It's probably taking a long time to get it permitted. Every state and every province is different. I don't know how long that's going to take, but I'm happy to work with it. And he's trying to interrupt me. No. Wait. You don't understand, dude. I got a blanket permit from the Canadian EPA. All right. I'm a big oil company. I can do what I want, and you're going to tell me what I need. So I said, okay. And I designed a system there. So we ended up, again, it was a class 3, class 4 soil was the best I could get from him because he's not a soils guy. All right. So water table was fairly shallow, about 18 inches deep. So we just bring in the farmer's till. We till the whole area. All right. I think it was over 4,000 chambers. We till it all in place. We bring in a foot of sand, put that on top. We throw chambers in a bed form, chamber, pressurize it, and we cover it with 4 feet of wood chips for insulation. 4 feet of wood chips, mulch, because they cleared out their, not tundra, but they're forest, and they had all these wood chips to get rid of, and it worked great as an insulation source. So anyway, just another funny one for you about dealing with engineers calling up on the phone not knowing what to do. All right, so that's really it. I want to let you know that Infiltrator are proud to be giving back to the community, and we're a corporate level sponsor for Habitat for Humanity. I've been on a couple of those sites. We do build days where we get the whole office to go out and build out. So, any other questions? Yes, sir.
What do you mean by pressurizing?
What did I mean by pressurizing? LPD, you know LPD? Low pressure dosing? That's what I mean by pressurizing. Yeah.
So you were using chambers with LPD inside the chamber?
Yeah, so the pipe is inside the chamber, yes. Yeah. Thanks.
I was wondering how you pressurize leaching chambers.
Yeah. Yeah. We need to think about, we need to patent that if we figure that out. Thank you.
That was great. Thank you very much. Thank you, folks. Lunch upstairs in the 3 rooms on the far side.
It's lunchtime this time.
It's lunchtime.